Okay, let me go to the whiteboard. All right, so again, here was the first law of thermodynamics. And so Q was equal to change in internal energy plus work done. Okay. So what this equation is telling you is the heat added to the system is equal to the change in internal energy of the system plus the work done by the system. Okay. Now we're going to talk about specific heats. Again, let me remind you, for solids and liquids, it's easiest to measure their mass. So we give the amount of heat added as this mass times the specific heat times the change in temperature. Okay. But for gases, what's easy to measure is the number of moles of gas you have. So what we have to define is the molar specific heat, and we define molar specific heats. And it turns out that when you add heat, what you want to, what the two processes that are easy to keep track of is heat added during constant volume and heat added while keeping the pressure constant. Okay, so this is the heat added while keeping the volume constant. And so this is number of moles of gas, and this is the molar specific heat at constant volume. And this is QP, while keeping heat added while keeping the pressure constant, and N is the number of moles. Okay, so CP is the molar specific heat at constant volume. Now, when the volume is held constant, the work done is zero. Okay, so the heat added goes all into raising the internal energy. When you're adding heat at constant pressure, work done is positive, and then you have to warm up the gas the same as constant volume, because you have to change the internal energy by the same amount. So heat added during constant pressure is greater because you've had to do work. Okay, so QP is greater than QV. Okay, so for an ideal gas, QP is greater than QV. Okay, and so what that implies is, of course, CP is greater than CV. Okay, and what we're going to show is okay, so you'll see in a few minutes, CP minus CV equal to R for an ideal gas. Okay, that's how much greater it is. Okay. So we'll define molar specific heats for gases because it's convenient to measure how much gas you have in moles. Okay. And so this is the heat added to the gas. The heat added to the gas goes into raising the internal energy, which raises the temperature and goes into any work the gas does. Okay. So here is an isovolumetric process. So these blue lines are isotherms. There's the temperature, and there's a higher temperature. You're heating the gas, so you're going from a lower temperature to a higher temperature. This is a constant volume process. This is a constant pressure process. The heat added during this process was less because no work was done. You had to add more heat in going from this temperature to that temperature because in this process you had to do work. And that's the constant pressure process. All right, so here's the heat added at constant volume, and here's the heat added at constant pressure. So this is the heat added during this process, and this is the heat added during this process. Okay, we sort of showed this on the last chapter, but let's do it again. So now we'll calculate, so we'll do a general calculation. So let's say each molecule has F degrees of freedom. Okay. So the internal energy of the system is the number of molecules times the number of degrees of freedom, and each degree of freedom contributes this much energy to the system if the system is at temperature T. Okay, so that's the equipartition of energy, and that tells you each degree of freedom contributes that much energy. So see, that's how easy it is to calculate the internal energy of the system. The problem is, of course, how many degrees of freedom are there? Okay. And that number changes for a given system, that number changes with temperature. Okay. But anyway, so there's the internal energy, E equal to N, yeah, and okay. So N, no, N K, K is the Boltzmann constant, is number of moles times gas constant. So this is equal to N F 1/2 RT. So that's the internal energy. And CV is defined as 1 over N del E by del T. Okay. And so it's 1 over N, and taking the derivative of this with respect to T, all you get, what you get is N times F times R by 2. Okay. So you get N times F times R by 2. So CV turns out to be F by 2R, where F is the degrees of freedom. F is the number of degrees of freedom. So that's CV. Okay. And that's the derivation that's shown here. So the internal energy is just for ideal monoatomic gas, it's just the number of molecules times that. And so the internal energy for an ideal monoatomic gas, the number of degrees of freedom is 3. And internal energy turns out to be that. So CV is 3/2 R. So for an ideal monoatomic gas, you have 3 degrees of freedom. Okay, that's what this is showing. So CV is 3/2 R for an ideal monoatomic gases. So all the noble gases are ideal, they're monoatomic. So this is our calculation, 12.5 joules per mole per Kelvin. What this number says is, to heat 1 mole of helium, you need 12.5 joules per degree Kelvin, or per degree Celsius or Kelvin. Okay, so if you want to raise the temperature of 1 mole of helium by 1 degree Celsius, you need 12.5 joules. Okay. So that was our calculation, and you see here is the experimental value, molar specific heat for monoatomic gases, all the noble gases, and it is indeed that. Okay, the experiments agree with your calculations. All right, so again, the general expression CV for a system with F degrees of freedom is F by 2R. For a monoatomic gas, this F was 3, and so it was 3/2 R. For a diatomic gas, F will be 5, and it'll be 5/2 R at normal room temperatures. At high temperatures, for a diatomic gas, that can be 7. Okay. All right, so for a constant pressure process, this slide goes through the derivation, and I will not go through the derivation. You guys can look it over. But what we prove here is Cp minus Cv equal to R. Okay, so the heat added in a constant pressure process is the change in internal energy plus the work done. Change in internal energy is when the temperature just rises, it's the same as in the constant volume process. And so if you go through this, you can see that Cp minus Cv is R. Okay. Now, this quantity, the ratio of specific heats, is useful to define because it shows up in various places. And so we define this ratio and call it gamma. Gamma is the ratio of specific heats. Okay, we'll have something to say about that in a little bit. So okay. All right, so okay, so here's what I want to point out about gamma. Okay, so gamma was the ratio of specific heats. And you see for monoatomic gases, gamma is 1.67. For diatomic gases, gamma is 1.4. And for polyatomic gases, gamma is less than that. Okay, so for these gases, it's 1.3. So what we see is gamma for more complex gases, gamma decreases. The more complex the gas, the smaller gamma is. Okay, so gamma tells you the complexity of the particles. Okay. All right, so for complex molecules, so for helium, you have only 3 degrees of freedom, and so CV was 3/2 R. It can only translate. For a diatomic molecule, it has the translational degrees of freedom, and then it has these 2 additional degrees of freedom. This third, so this is rotation about that axis, this is rotation about this axis, this is rotation about the third axis. It's just that it takes a lot of energy to get the molecule rotating about that axis, so that degree of freedom is essentially not in play. So for a diatomic molecule at normal temperature, you have 5 degrees of freedom, 3 translational degrees and 2 rotational degrees. And so Cp is 5/2 R. And Cp, of course, is Cv plus R. And so it's 7/2 R. Gamma, the ratio of Cp by Cv is 7/2 by 5/2, which is 1.4. Okay, so that's what we were saying there in this slide. Gamma for diatomic gases are 1.4. That was our calculation, and these are the experimental values, okay, which you can see agrees closely with theory. Yeah. So for a complex molecule, you can rotate it about all 3 axes, so the number of degrees of freedom would be 6 for normal temperatures, and when vibrational modes come into play, then a higher number of degrees of freedom come into play. So at normal temperatures, it's 6 degrees of freedom, and CV is CV is 6/2. 6/2 R, just 3 R. Okay. And so Cp is 4 R. Cp by Cv is 4/3. 3.33. Okay. And you see that here. Oops. So roughly 1.33. Okay. All right, so for complex molecules, so for diatomic molecules, since that degree of freedom is not available, gamma is 1.4. Okay, so here is showing Cp for a hydrogen gas, Cv for hydrogen gas at various temperatures. Okay, so again, like Cv was F by 2R. Okay. F is the degrees of freedom. And we're doing this for a hydrogen molecule, which is a diatomic molecule. So here is the graph. We've seen this graph before. CV as a function of temperature. So you take hydrogen gas, and if you're below 100 degree Kelvin, CV is 3/2 R, meaning it only has translational degrees of freedom. So this molecule is not rotating. All it can do is translate. Okay, so it's the temperature are too low to excite any of the rotational modes. Okay, so these two rotational modes are not excited. And of course, we never excite that rotational mode because that requires quite a large temperature. Okay, so even at, so what this graph is showing you is below 100 degree Kelvin, none of the rotational modes are excited, and it has only translational degrees of freedom. So around room temperature up to 1000 Kelvin, the rotational modes are excited. And then above that temperature, the vibrational modes are excited. And so for a diatomic molecule, there are 2 vibrational modes. So here's 7/2 R. Okay. So again, for these low temperatures, the degrees of freedom are 3. For these temperatures, the degrees of freedom for this diatomic molecule is 5. And for these temperatures, it's 7. The degrees of freedom is 7. Right, so that's what, so the specific heat varies with temperature because the number of degrees of freedom changes. Okay. For an adiabatic process, now we're going to show, well, as I said before, PV to the power gamma is constant. Again, this is for an ideal gas. So here's an isotherm, the blue curve, and that is a higher temperature than this. So if you go through an adiabatic process, you're not exchanging any heat with the environment. And so this was an expansion, so the gas cooled. Okay. So a good example is when you pump bicycle with air. When you're pumping the air, that's an adiabatic process because you're pumping it fast enough where there's no chance to lose heat to the environment. Okay. Anyway, so here's an adiabatic expansion and the gas cooled. And what this equation is saying is PV to the power gamma is constant throughout this curve. So for every point, you can calculate PV to the power gamma, and what you'll find is the same value. Okay. And this goes through the derivation of it. And again, I won't go through the derivation. Okay, so again, what we're saying is PV to the power gamma stays constant. Okay, so on the entire, during the entire adiabatic process. Okay, so PV to the power gamma is constant, and you can use the ideal gas law and derive this. So TV to the power gamma minus 1 is equal to TV is also constant. Okay, so along that curve, TV to the power gamma minus 1 is constant. Okay, remember T is also changing on that curve. T along this curve does not change, but along this curve, T is changing. Okay, so now what we're going to show is the exponential atmosphere. Okay, so let me do a diagram first. Okay, so imagine, oops. Okay, imagine the slab of air. Okay, so again, right above your head or whatever. Now, since this is not falling down, this slab of air has a weight. Since this is not falling down, there must be a force below and a force on top. Okay. So the force So what we're saying is the rest of this gas, the pressure due to this gas is holding this slab of air up, okay? And the pressure due to this air is pushing the air down. So this force must be greater than that. And this force, the pressure below, the force below minus the force at the top should equal the weight of the slab because the slab of air is not falling down. And this force below is the pressure below times the area minus pressure at the top times the area equal to mg, equal to the weight of the slab of air. Okay, so that's what's holding the slab, this slab of air up. Okay, so what we're saying is the pressure at the bottom has to be greater than the pressure at the top. So as you go up in the atmosphere, the pressure has to decrease. And so here's the ideal gas law, PV equal to nRT. Okay, we will not change the volume, we'll consider the same volume. So, and what we'll assume is the temperature doesn't change as we go up. That's a simplifying assumption. The temperature does change, but we'll keep it constant. So PV equal to, okay, so V is constant, T is constant. The only way the pressure would change is if the density, the number of moles per unit volume decreases. So the way as you go up, the pressure decreases because the density of molecules decreases. And that's what's shown here. So again, so the weight of this slab, there's the weight of that slab being supported by the higher pressure at the bottom. So dP has to be negative. So this is the upward force, that's the downward force. Okay, so negative or negative would make this positive. So what this shows you is, so dP cross A times A is mg nV a dV. Anyway, you can go through the derivation. Okay, and so what you find is the number density, like we said, as you go up, the density of molecule decreases. Okay, nV is decreasing. Okay, there are fewer and fewer molecules in a given volume. And it decreases exponentially. Okay, so by the way, we look at the distribution of the molecules in the atmosphere assuming constant temperature. So that's the simplifying assumption. The temperature, of course, is not constant, but that's what we'll assume. And so the number density decreases exponentially. It's n naught e to the power of minus mgy kBT. All right, so that's an interesting expression. So let me write this down. Okay, so what this expression is saying is the density of molecules at height y is the density at height 0 minus e to the power minus mgy. So that's the potential energy of that of a single molecule at height y divided by kT. Okay. So this is potential energy, and that's kT. Okay. So, by the way, so let's look at this expression and so you can put in the numbers. So here is the weight for one molecule, of course. The air is nitrogen and oxygen, so you can take a weighted average. So here would be the weighted average. So nitrogen has 28 atomic units weight, so nitrogen is 28%, and it's 78% is nitrogen plus oxygen 32%, 0.21. So atomic units, that's the weighted average for M. So M is equal to that. Yeah. So, and then you can convert that to kilograms. But there's the potential energy of a single air molecule divided by that. Okay, so you can put all those numbers in the temperature of airs. You can take it to be around 300 degree Kelvin, okay, or a little less. So you can put those numbers in, And what you find is that at about 8 kilometers, the density falls to 1 over E, which is, so what you're saying is, so that this expression reduces to, so Y in kilometers, this is the density at ground level, E minus Y over 8.1 kilometer. Okay, so that's what we're saying on the slide there. So, and Y, of course, is in kilometers. Okay. So, at 8.1 kilometers, the density is 35% that of ground level. Okay. So on top of Mount Everest, which is higher than 8 kilometers, the air is very thin. It's only 35% the density at ground level. In Denver, which is a mile high, the air is about 80% the density at Daytona Beach. So this exponential factor gives us an idea, and it's suggestive. Okay, so it turns out that it's true. It turns out that what this Boltzmann distribution law is telling you is the following. So let's say you have a system which has various energy levels. So, okay. And you ask, what is, so if you have a system with many particles, what is the probability of occupying any of these energy levels? Okay. So this is, okay, so there are the energy levels. Ground state energy, first excited state, second, third, fourth, fifth. Okay. So if you ask, what is the probability that a system will occupy this energy I, and the probability, what the Boltzmann's distribution law says is proportional to EI by KT. Okay. So that's the important relationship. So higher the energy, lower the probability. Okay, so it's, and that's the Boltzmann's distribution law. So the Boltzmann's distribution law tells you, so the number of particles in this, at this energy level are the total number of particles times e to the power of minus E by kBT. Okay. So this is the Boltzmann's distribution law, and it's a very important law, okay, which is useful in calculating the energies of various systems. All right, that finishes this lecture. Okay, again, let me briefly summarize what we learned. So we saw the first law of thermodynamics, which states the change in internal energy is Q minus W. Okay, so the change in internal energy is equal to the heat added to the system minus the work done by the system. We learned about isothermal processes, isothermal processes where temperature remains constant, isobaric process where the pressure remains constant, isovolumetric process where the volume remains constant, and an adiabatic process where no heat is exchanged. Okay, and then we saw the probability of an energy level being occupied is proportional to that. That's the Boltzmann's distribution law. Okay. We also saw that in an isovolumetric process, we also define gamma, the ratio of specific heats. Okay, and you saw that gamma is 1.67 for a monoatomic gas, 1.4 for diatomic gases and 1.3 for polyatomic gases. Okay. This is at normal temperatures, room temperatures. Okay, and then we saw the Boltzmann's distribution law. The probability of an energy level being occupied is proportional to minus E by KT. All right, so we will stop now.